Now, what kind of data is trapped in ice that can give us information? Well, the type of data that's trapped in ice is the concentration of carbon dioxide and the amount of deuterium to hydrogen ratio. All right, and so let's look at this. This is ice core data. This particular data goes back, this is time 0. If you look at this graph, just orient yourself for a minute. This is time 0, like now, and it goes back 160,000 years. So 160 millennia or 160,000 years back in time. That's from ice core data. And what they do is they can take the ice and very carefully separate the ice and then put it in a container and measure the concentration. There's little air bubbles trapped in the ice. They can measure the concentration of the carbon dioxide. So this is the carbon dioxide concentration in the little bubbles over time. And they see how if the concentration of carbon dioxide in the bubble, that must indicate, you know, the concentration of carbon dioxide that was in the atmosphere at the time, that the snow fell and then was compressed into ice over time. Then down here, the other thing that they do is they look at the temperature. And the temperature is inferred by the deuterium to hydrogen ratio. All right. So I'll tell you a little bit more about that in a minute. But for now, just look at the correlation. I mean, you can just glance at this and see that when this goes up, this goes up. When this kind of goes down, this goes down, and now it's going back up again in recent time. And so this being the temperature, this is the difference over the average temperature. The average temperature would be 0. We consider this like the 0 line. So this is how much above or below the average temperature existed at that time. And the average temperature, they're taking the average between 1950 to 1980 average. Whoops, 1980 average. All right, so this would have been at the 0 line. This is the average global temperature averaged over the time from 1950 to 1980. That's what we get to 1980. All right, and so you see that 160 million years ago, 160,000 years ago, the global temperature was 8 degrees colder than it was between 1950 and 1980. But then 130,000 years ago, the temperature was about 2 degrees greater than it was 100 than it is now. Okay, and then you can see that there was a sharp decrease. Well, not how sharp is sharp. It's over 20,000 years. It decreased, and then kind of some fluctuation, and then a minimum 8 degrees below the average again about 20,000 years ago. And so these minimum are correlated with ice ages, all right? And so there is some obvious fluctuation that's going on over time. But the interesting thing is that fluctuation has been correlated into the concentration of carbon dioxide in the air. And so over the last 20,000 years, the carbon dioxide concentration has steadily increased, and the average global temperature has steadily increased, all right? And you can see here's current time, a little bit higher than the 1950 to 1980 average. All right, so there's some data that's correlating the concentration of carbon dioxide over time with the temperature, and the temperature is inferred from this deuterium to hydrogen ratio. All right, so what does that mean? Just for a second, let's just see what they're talking about here. All right, the deuterium to hydrogen ratio. What they do is they look at the water, and in any sample of an element, there is some natural abundance of different isotopes, and for hydrogen, actually, the element hydrogen, 99.99% of elemental hydrogen is in the form of the isotope that we call H1. That particular isotope has no neutrons and just 1 proton. But 0.01% of the naturally occurring hydrogen in the world is deuterium. We call that H2. H2 has 1 neutron and 1 proton. All right, so because of this natural abundance, then any hydrogen that's found in any compound that contains hydrogen, 0.01% of that hydrogen is going to be in the form of deuterium. So in the oceans, for example, there's a lot of water, so there's a lot of hydrogen. So, excuse me, most of the hydrogen is in the form of H1, but a very small percentage is in the form of deuterium. So what that tells you is that most water is just a regular old oxygen and regular old hydrogen. And so we'll just put ones up here just to indicate that we're talking about the isotope hydrogen 1. But a very small bit of the hydrogen in water is going to be deuterium, in the form of deuterium. And because the mass of deuterium is twice the mass of hydrogen, it has a mass number of 2 as opposed to 1, then water that has deuterium as its hydrogen is heavier. Okay, so you could call it heavy water. And what happens then is that, in the oceans and the lakes and whatnot, where you have all this water, the water is evaporating. The lighter water is going to evaporate at a faster rate than the heavy water. But then, so too, the heavy water is going to condense faster than the lighter water. And so there is a correlation to do with temperature, evaporation, and condensation. And scientists have worked it out so that they can actually correlate the deuterium to hydrogen ratio in ice is going to change depending on what the temperature was at the time that the ice was formed. Now, in the Arctic, the ice was formed from snow. It fell in the form of precipitation, and then it packs down, and the snow changes into ice with pressure. So, we aren't going to understand completely how that's done. That would take like an hour to explain it. But the bottom line is that scientists, because they know the difference between deuterium and hydrogen, they know the abundance of deuterium, what it should be under completely natural conditions, they can then predict this ratio is going to change slightly depending on the temperature at which the water was evaporated and the water fell back to snow. That's how people can infer temperature from the deuterium to hydrogen ratio found in the ice from the ice core. Okay, so there's legitimate science that can help people predict all the way back, 160,000 years ago, what the temperature was at the time that the snow was formed.